We are going to have the lectures 27, 28, 29 and 30 combined in these slides. Okay, so this session we are going to mainly discuss from the chapter 9 of the book I mentioned. Okay, so in the chapter 9 it says the photovoltaic systems includes both isolated and grid connected modes, various issues of that. So here in lecture 27 and 8 you can see some part have been discussed in the previous slides, like impact of temperature, insolation, effect on the IV curves, we saw that, but we are going to discuss like the MPPT, and then you can see that in the next lecture 29 and 30 what we are going to discuss, standalone photovoltaic systems, estimating the load, how we are going to estimate the load for the standalone photovoltaic systems, battery storage sizing, optimal sizing of renewable energy sources in microgrid application, capacity factors, PV connected grid systems and its economics. So this we are going to discuss based on the chapter 9 of the book I mentioned, and these are like in one session. So here basically what are the contents we are going to discuss. The development in the PV technology, we discussed, renewable energy integration, we gave the nice overview, and then some part already we discussed, like some standard test conditions, etc. Then we talk about this photovoltaic system. Some part we find a little bit repeated. We will quickly go through it. Then when we have these IV curves for photovoltaic system, then what are the other components like the loads? So loads could be different types. Resistive load, it can be DC motor load. We have the battery storage system, and then we talk about these IV curves, the MPPT trackers. Then we talk about the grid connected system, interfacing with the utility, capacity factor for grid connected system, grid connected system sizing. If you want to decide what should be the size of PV systems, how we are going to decide, we will discuss. Then standalone system, batteries, battery storage capacity, battery sizing, blocking diodes. We talked about the blocking diodes in previous topic as well. Then how we decide the sizing of PV system for standalone microgrid or standalone PV system. And then we briefly touch upon some issues. Of course, we have done this in the very first day as well. So this is what we are going to discuss. So we expect to complete this in 1 or 1 hour 30 minutes, depends upon how we move forward. Okay. So if we see the development of PV installations, so initially PV systems have been small size, okay, uh, and like the distributed. Then around year 2010, uh, until 2010, majority of PV systems were connected small size distribution level. In recent year, because of the drop in the cost, we have started talking about the large photovoltaic system. And if the power rating for the PV systems is significantly higher, and then obviously we will be connecting them at higher voltage level depending upon the size. PV system integration in the subtransmission or transmission system. So this slide a little bit old. In this first part, I showed you that by end of 2023, we already have more than 1600 gigawatt of the installed capacity worldwide from photovoltaic system. You can see the trend that mainly you can see PV system started integrating around 2008, 2009. But thereafter you can see how exponentially growth of the PV system is there. Particularly in the last 4 or 5 years, you can see how exponentially this PV installed capacity worldwide is growing. So if you see the cumulative growth rate in photovoltaic systems worldwide, 2016 say until 2022, so this growth rate has been like 32%, lower side 23. So if you take as an average 25%, so within a period of 4 years, the installed capacity worldwide, it will just become double. In fact, as the cost comes little bit more down, there will be more and more significant capacity addition. So within a period of 3 years, so the installed capacity can be double as well. So as such, we do not see any barrier that why we cannot have even more than that capacity addition. Of course, whatever is the revenue needed, that has to be arranged either government or whoever is installing. But other than that, we don't see any negative aspect from the PV system. Okay, so it has almost all positive features. Okay, so in future we can see that the capacity addition will be even faster. The cost has come down, and all things are in favorable of photovoltaic system. So this slide we already talked about that when we are integrating PV system. So at which level we should be integrating, either in the distribution or in sub-transmission or transmission. So, or at what voltage level. If we have very small size PV system, individual house, so if the house is small, we will just connect them at the voltage 230 volts. Okay, of course with the application of power conditioners, inverters. But if it becomes like a large farm, I give an example that PV systems in our country we have more than 2000 megawatt capacity. If you are going to, uh, generate 2000 megawatt power, okay, so voltage you have to go for higher level. It is the simple equations. Power is equal to voltage multiplied by current. Okay, if voltage you keep it very less, for example, you want to generate power 2 megawatt. If voltage you think that 230 volts, think of how much will be the current. Okay, same thing. What it applies, transmission of power through the transmission line. Okay. So if amount of power to be transmitted is significantly, significant, huge amount of power you want to transfer, then obviously you have to increase the voltage. If you don't increase the voltage, that current will be very high. If current is very high, then your transmission line conductor will be very thick. Okay, it will add more cost on the conductors, transmission towers. So basically, when we are designing the power systems, we see that two important considerations are there: voltage and current. So we should have suitable voltage, suitable current. Okay. How much current we can carry through the wires, conductors. So accordingly, we have to select the suitable size of conductor, wire size. If current is less, we will select the thinner size of conductor. If we have more current, we will go for the thicker wire. Okay, if you try to pass huge current through thin wire, it will melt down. Okay, as simple as that. Then what about the voltage? Whether voltage is low or high, accordingly we have to provide the amount of insulation. Here I am talking about the insulation, not insolation level. Okay, so insulation level, for example, if you are using the wires for 230 volts, you will have this thing. But if you have the cables, for example, 11 kilovolts, okay, so you can see how much insulation level we are using. Like these cables can be used for 11 kilowatts? Obviously no. Okay, so depending upon the voltage level, we will have the higher amount of insulation in case of cable. Even if we have this transmission conductor, overhead conductors, what we are doing, we are keeping the appropriate spacing between the conductors. Insulation is the medium. So we have to select the appropriate voltage. As I mentioned, if the power being generated is significantly higher, then we will connect in the sub-transmission or transmission system. Then when we are integrating power system, then we see some other issues. Power electronics. Power electronics means the converters. You saw the role of converters is very important in the renewables. Whether this PV system is isolated or grid connected. So role of storage system is very important. Power quality issues. When we are, having the converters, it is very much essential in the renewable energy. But when we have converters, you see some power electronic issues can be generated, harmonics, etc. So we have to be careful about that, like how we reduce the harmonics using the filters. So all these things have to be taken into consideration. What sort of issues we are going to consider when this PV system is being integrated. If it is a small system, we consider the issue like the moving clouds effects. if it is medium size, for example, if the government decide that most of the people have their own PV system, okay, government increases, government gives the rebates that okay, we will give you some rebate, you can have your own PV system, okay. So in that case, what could be technical issues? Okay, so as you will see that during the midday, say around 10 to 3, you will have maximum power generation from PV system. Okay, and obviously you will see that during that day, midday, in residential areas, the load will be minimum as people go for work, children go in the school. Okay, so load in the home is minimum. So generally you will see that power generation is maximum. Power generation is maximum from PV, but load is minimum. So there is difference, significant difference in the generation and demand. So that can lead to have some issues about the frequency regulation or voltage regulation. Okay, when there is significant capacity addition in localized area, so it can have some frequency and voltage regulation issues which needs to be considered. If you have large size PV plants, I explained. So with the large size PV plant, basically what we are doing here, we are essentially replacing the synchronous generators being used in power generation, coal, gas, nuclear, large hydropower plants. So these rotating generators are being replaced by the static PV generators. Okay. As you know, this rotating generator will store the kinetic energy, and that kinetic energy is used when there is sudden disturbance in the power system. Okay. If there is sudden increase in 500 megawatt load, okay, so from where this load will be suddenly met, electrical system is not going to wait. It just needs the very instant. Okay, so whatever energy stored in the as a kinetic energy in the generator, that will be used for the instant purpose, and then thereafter system tries to stabilize, and fuel input can be increased to have matching of the sudden increase in the load. So these are some of the very briefly some of the key issues we talked. We examined a PhD student, the student first say, Rakib Shah. So he studied the stability challenges for large integration of PV, large size PV integration. So he started his PhD around say 2011. When he submitted his first paper, then he got the comments from one of the reviewer that authors, what they are thinking, large size PV plants, it's just like the imagination, that even in the 2011 you will have hardly large size PV plants. Okay. So you can see how fast this PV technology has been there. Then in few years, you can see how much significant large size PV plants are coming up. Okay, so the first paper you can see very nice review paper discussing about the key power system stability issues for the large scale PV integration. So this is very nice review paper, has attracted large number of citations. Then you can see some other interesting paper dealing with the stability analysis, damping performance analysis using the battery and energy storage system, ultra capacitors, shunt capacitors with large scale PV system. And then you can see that the last paper, it says that oscillatory stability analysis with high penetration of large scale photovoltaic systems. So as I mentioned, we tried, in most of the cases, we try to have target the high quality, high impact journals. So all you can say 3 papers published are in Elsewhere journal, Elsewhere Science Direct journal. So they have quite high impact factor, like renewable and sustainable energy issue. I think now this is around 16 or like that. Applied energy conversion and management. So impact factor around 9 or 10. Okay. So the very nice study done by the student. Okay. Then I already mentioned that at University of Queensland, we have initially we built up 1.2 megawatt PV system on the main campus. Thereafter, it was expanded in other campuses as well. So the total capacity was 5 megawatt. So here you can see that previously we used to have, like, through this link. So previously through this link, in real time you can see this graph, how is the weather, how solar electricity generation is taking place. Okay. I'm not sure whether we can see in the real time or not. I have not tried. Then you can also see that some other information, very interesting information you can find on this website about the practical experience of the photovoltaic systems, like what type of PV systems have been used, what is the storage technology, etc. So you can get very good practical experience, learning lessons, outcome from these PV systems. So you will find a lot of interesting information, white papers on this website. Okay, so some of the slides coming repeated, but it's okay. So we are just trying to little bit revised explain you, because the topic is really very interesting. So as I said, the configurations, we can have 3 configurations: grid connected PV system, or PV system is very small, can be mounted on the pole, or PV system can be placed on the rooftop of the building, or this PV system could be integral part of the building, what we call as the building integrated PV, BIPV. So some place, maybe if you would have visited IIT Delhi, have anyone visited? So you can see, like, one of the building in front of a library. Have you seen anyone? Yes? You notice that roof is PV material. Eh? So it could be building integrated PV. Okay. Then we have this standalone. In standalone, we have to be more careful about the backup. So backup batteries, then diesel generator, optional, may or may not be there depending upon the situation. So PV system, isolated configuration. We talked about the PV system, this configuration, like its application in the agriculture system. So in agriculture systems, like the country like ours, so we have huge farmers. There is need for this water for irrigation purpose. So if we have tube wells, how we are going to extract the water from the ground? So we can use this PV along with DC motor. We do not want to use the battery to have the low cost from the PV system. Even not inverters. We want to have simple system, very robust, low maintenance and least costly. Okay. So this configuration, like as the water pumping for irrigation application. So whenever we have this solar sunshine, it will run the DC motor and water we can use. So even doesn't it matter, like say moving clouds comes, so if it is stopped for half an hour, 1 hour, it's not big issue, right? Because the water we need is for irrigation purpose. Okay, so it doesn't need that we need the continuous power. So whenever it comes, it's good. Okay, so that way we want to have low cost solutions for the farming applications. In fact, one PhD student did PhD around this topic, water pumping applications based on PV. How I know? I was the examiner for the thesis. So he did quite good work. Some related with more kind of practical experience, like how many water pumpings we have, some practical data. He was maybe working in some industry as well. Okay. Then we already saw the IV curve. We already saw the IV curve of the PV system. As I said, it is not only one IV curve, but there are several IV curves as the insolation level changes. Now, where we will operate our power system. Okay, so we will have load. What is the nature of load? Okay, so say this is your load curve, where the load curve and photovoltaic IV curve will be crossing each other. That is the operating point. Okay, so obviously we will be interested that operating point is closer to the neck of this IV curve. Corresponding to the neck, it is the MPP. So from here you will see the concept of maximum power point tracker. Okay. Now we little bit try to understand the components we are using in the PV systems, like the load, different type of load, then battery storage system. Okay, so here if we have, for example, resistive load, this we can simply do experiment in the laboratory itself, very simple. So you have got PV panel, one or more, then you have got the potentiometer, rheostat, a variable resistance. So by varying the resistance, increasing, decreasing the resistance, you can change the current. Okay, so you can have the different currents depending upon how you increase or decrease the resistance. So what does it mean? That you can have this line, you can have this line, depending upon how much resistance you are making. So 1 by R here, it says the slope. Okay, so you have some flexibility where you can operate your system. If the resistance is this, you are operating here. Okay, if you have this resistance, you are operating here, or if you have this resistance, you are operating here. So obviously our interest will be operate corresponding to this point MPP condition, which is obvious. So in general, we know that voltage is equal to current into resistance. So when we are talking about when we want to extract the maximum power from the PV, so obviously the value of this resistance corresponding to maximum power, it will be voltage, we say that Vm, current is Im. So we have this point corresponding to MPP condition. Like wherever you see neck is there, from the neck point you have dropped this line vertically and horizontally. Vertical line is your Vm, maximum voltage and maximum current. So as we talk, as insulation level changes during the day, very early morning, 10 a.m., 11 a.m., 12, 2, 3, 4, 5. So you'll see that sunshine keeps on changing, insulation keeps on changing. In the early morning, we have lower insulation, say 200 watt per meter square. Okay, around 10, it can be 400. Okay, this way it will increase when we have higher insulation level, and then afternoon again it starts decreasing. Okay, so now you'll see that we don't have one IV curve. Okay, we have the several IV curves, say 5, 7 IV curves, what you are seeing in this figure. So for each of the curve, you will see that where is the MPP for each curve. Like for this one, you are seeing this neck point. Here, this one. Here, this one. Here, this one. Here, this one. So basically, even MPP you want to do manually. Okay, through the resistance you can try to adjust, say corresponding to this point. Okay, but as some time changes, it will not stay corresponding to MPP point. So you have to be continuously keep on tracking the insulation level, so that we can operate our load corresponding to MPP condition, we can have maximum output from the PV system. So this MPP obviously needs to have automatic, not manual, because manual controlling not very accurate and difficult. So obviously we will have some device which it can keep on doing automatically. Okay. Now let us little bit understand the DC motor. We use, for example, irrigation PV systems for water pumping application. So its characteristic in the starting, it will have, as we have any motor, it will have generally high current. Okay. Then once motor starts, its currents will decrease. So you can say that this is a DC motor current versus voltage IV characteristics. So here you will see that when we are using the same application PV system for irrigation application, DC motor, now you can see that DC motor characteristics, here DC motor is the load. Okay, so this IV characteristic we superimposed on the photovoltaic IV characteristic. Okay. So for this motor to start, how much insulation level we need? For starting, it needs around 800 watt per 400, you can see starting current. So it needs the insulation level of the order of 400 watt per meter square. So say for example 400 watt per meter square, it will generate say around 10 AM in the morning. Okay, but we want to have the say very long duration application for water pumping application. Okay. So what we want, that if motor can somehow be started corresponding to say 200 watt per meter square level. So for example, here it is 10 AM, here it is 8 AM. If you want to have long hour of operation for the DC motor, so how you can do that? Okay, so here basically what we are doing here, we are placing one more component called as the LCB. LCB stand for linear current booster. Linear current booster. So it can help, like say MPPT condition. So the current, it can reduce the DC motor current. The motor can be started corresponding to reduced current. So you can see that if we are using this device LCB, motor can be started closer to say 8 AM in the morning. So motor can have the extended hours of operation. So this way, linear current booster or any device similar to that can be very useful. Now we little bit understand the IV curve of the battery, as battery are very essential part for the PV systems. So energy is stored in the batteries for off-grid applications. Now what will be the IV characteristics or some important information for the battery? So battery, what sort of equations we have? Batteries. So here you can see that batteries, we have some initial resistance, then the voltage, what you call as the across the terminal of the battery, and what you measure like say across the panel. So there will be some, they will properly related with the voltage drop terms. Okay, so here this voltage you can see V PV panel V will be equal to VB plus I into Ri. Ri is the say internal resistance of the battery. So you can see that IV characteristic of battery is just like say you can sort of straight line, okay, theoretically. Now changing the IV tilt line with a slope of 1 by Ri, applied voltage must be greater than VB. Discharging IV line tells to the left, tilts this discharging battery IV line tilts to the left with a scope of 1 by Ri. So you can see here what are the characteristics during charging, during discharging. So during charging they are tilted like on this, little bit on the clock, means on the right side, whereas during the discharging it is tilted slight bit on the left side. So this is IV characteristic of the battery. Now very simple example, what you are talking, you have the battery. If battery you connect to the photovoltaic panel, okay, so in that case obviously which direction current will be there, either from battery to the PV or PV to the battery, which direction current will flow. Current has property to flow from the higher voltage to the lower voltage. So accordingly there will be an appropriate current. So here you can see in this some simple example. It says that you have a nearly depleted 12 volt lead acid battery which has open circuit voltage of 11.7, internal resistance of 0.03 ohm. What would be the PV module operation if it is delivering 6 amps to the battery? Then if 20 amp is drawn from the fully charged battery, with open circuit voltage of 12.7, what voltage would the PV module operate? So very simple example, just you are using in A part, the PV voltage will be, the voltage P will be equal to VB plus RI into I, or very similar, you are finding this, so which is explained here. Now let us talk about the MPPT, the concept of maximum power point trackers. So it says that efficiency gain can be significantly realized if the operating point for resistive DC motor, battery, etc. Could somehow be kept near to the knee of PV IV curves throughout the ever-changing daily conditions. Like as you see, insolation keeps on changing, so IV curve keeps on changing. So you want to keep the, operation of the system corresponding to knee point. Okay, so when you operate the device corresponding to knee point, we call the device as the MPPT trackers, which track the position to keep the load closer to the knee point. Okay, so here in the next slide you'll see that the circuit in the next slide is combination of two circuits and is called as the buck and boost converters. A buck and boost converter is capable of raising or lowering the DC voltage. So you can see that you have a converter, which could be buck converter, boost converter. So you have got the PV system, sources, then DC motors, and then of course in between we have the we are using the converter, so which is basically a high frequency switch, inductor, capacitor, and the diode connected in the reverse bias. So this boost converter called as the MPPT. So this MPPT, the switch we mentioned in this circuit, so this switch is not the simple switch what we are using in this our electrical systems. So this switch is a transistor or FET switch which flips on and off. It is on and off at rapid rate of the order of the 20 kilohertz, while the load is this transistor switch, my apology, this transistor switch, electronic switch based on the IGBT or FET, field effect transistor. It is electronic switch. So it flips on and off uh, at a rapid rate, 20 kilohertz. So this is not the ordinary switch, but it flips on and off rapidly. So with this switch on and off, how much duration this switch is on, how much duration this switch is off. So from there we have the concept what we call as the duty cycle. I will show in the next slide. So you can see that how in one cycle, how much duration we can keep the switch on, how much duration we keep the switch off. So this we can adjust, we can change. So we can have this on time greater than the off time, or we can have opposite to that, or both we can adjust equal. So this duty time, duty cycle can be adjusted. So what does it means? What is its effect? So here the voltage, one side you have from the PV panel, other side you have on the load, in between you have got the converter. Okay, so you switch. So this switch, by adjusting the switch duty time, you can change the the voltage across the output. Okay, so here I'm not going into too much of the detail. Here, as you can see, the D. So here in this clearly you can see B part here, D is 0.5. Half of the time the switch is on, half of the time switch is off. Then here you can see that on time is lesser than 0.5. Here it is more. So accordingly, I'm not going into this technical or long-term discussion, but the concept is very simple. You have the output voltage, input voltage. What you'll see basically, how much time the switch is on, how much time the switch is off. You see in the converters, you have the inductor, you have the capacitor. So these inductor and capacitor will store the energy. You can see that when the switch is closed, current is flowing. Switch is closed, current is flowing through this. Okay, so this circuit, the diode this direction, right? So inductor is energy stored. Then when you switch off, that whatever energy was stored during when it is off, that energy should be dissipated. So whatever you say, when the switch is on, how much is power stored, then the same should be dissipated when the switch is off. So both these power you can just make equal. And when you simplify this equation, so the ratio of output by input, simply you can relate with the only quantity D, which is output by input voltage will be D divided by 1 minus D. So here negative sign is not of very concern or important. So you can easily see the relation between the output and input voltage simply by the term D. So interestingly, for example, you can see this example that we have a PV module. Its maximum power is at Vm is equal to 17 and Im is equal to 6. What duty cycle its MPPT should have if the module is delivering power to 10 ohm resistance? So you'll see that maximum power will be maximum voltage multiplied by maximum current. So given here, maximum power will be 17 multiplied by 6, 102. So that maximum power you want to deliver to the resistance of 10 ohm. So for delivering of this maximum power to 10 ohm, again you know the relation that power you want to transfer 102 watt in the resistance 10 ohm. So you know the relation P is equal to V square by R. So it gives you this voltage across the resistance, voltage across the load as using this power 102 resistance of 10 ohm. It gives you the voltage across resistance 31.9. Okay, so you have your input voltage 17 volts. This maximum input voltage 17, maximum current 6, then maximum power 102 that you want to transfer across this load resistance. So what should be the voltage across the load, output voltage. So this voltage you saw that it is 31.9. Now duty cycle we need to find. So simply you can relate with respect of this equation. Output voltage divided by input voltage is simply equal to D divided by 1 minus D. Minus sign you can simply neglect. So it gives you the value of D is equal to 0.65. So here you will see that when we want to have output voltage higher than input voltage, then the value of D will be higher than 0.5. If you want to have output voltage lower than input voltage, then D will be lower than 0.5. Okay, so this boost, it will simply act like the MPPT because it can transfer the maximum power. So it basically explains you the concept of MPPT. So some of these things, for example, when we have the grid connected photovoltaic system. Okay, so in grid connected simple small photovoltaic system, what sort of components we have? If your small PV systems, like here in the Department of Electrical Engineering, your small PV system, you want to connect to the grid. So what sort of these components we have got? Of course, you have got the several PV panels which will be connected in series and parallel to get the required voltage, required current. Then you have basically a sort of the box, what we call this box, a combiner box. It includes like the diodes. These diodes we call it the blocking diodes for each array. Okay, and then you have got like the fuses if there is overcurrent, so it can protect. Like here in our system, we have got the MCB. So fuses, then you can have little bit more what we call as a protective device, like say lightning surge arrestor. So this way you have a standard combiner box. Then you can have some device called as the array disconnect. If any of the array you want to disconnect, you can have the array disconnect. Then you have basically inverter, DC power being generated by the PV systems to make it AC before feeding into the grid. So you have the inverter, then you can have a breaker to connect or disconnect if needed this PV system from the grid. Okay, then you are feeding this power. You can have grid connected system. You have this home or some load. The power produced can be utilized by the home. Excess power can be fed into the grid through the net metering scheme. If home needs more power, power can be drawn from the grid. So there is a concept of net metering. So the meter can rotate in the both directions depending upon the direction of power. So here these are the some of the components you will see in a grid connected PV system, but I explained if you have small PV systems like here, few panels, and you want to connect the grid, the components needed. If you have PV systems like a very big farm, PV farm, obviously components will be more and complex. Okay. Because as we have bigger system, then we can incorporate some bigger and complex systems for protection and so many other stuff. Okay. Now the concept comes that when we are using these PV systems, how many inverters we have, whether we have many inverters or lesser number of inverters. Okay, what is the choice? So if for example in the previous slide I showed you like say one inverter, or you can have several inverters of small size. Both will have some pros and cons. If you have individual small inverters, it can allow easy expansion. The connections, distribution panels are simple, need the less expensive cabling system. Or if you have a bigger system, then it can be economical, it can be less costly. Okay, like if you have say 10 small inverters, whatever capacity is there, if you have like one bigger, so obviously single bigger size inverter cost will be less. So both have got some pros and cons. Now when this PV system is interfacing with the utility, obviously there is concept of net metering. In principle, customer will pay for the amount of the energy that PV system is unable to supply. But there should be a kind of proper what you call the MOU. Okay, if the utility agrees and they are willing to pay. If they say we don't have provision, we don't pay anything. If you wish, you can. Okay, so is not something. So and then again, it could be, when you are taking from the grid, how much is the price? When you are feeding the power into the grid, it may not be at the same. Okay, so there could be difference as well, because they are managing, they have more overhead charges. Okay, so when you are buying, costly. When you are feeding, you may be giving the cheap supply. Okay, even if some nominal difference is there, not a problem, but it should not be there that you are just giving for the charity purpose. Okay, at least something is there. No, when you are regularly and consistently in some significant quantity you are doing, then it cannot be free. So in the event of outage, PV system must quickly and automatically detect from the grid, as we said that renewable power system. Okay, so now renewable power plants have been developed significantly. They are not immediately disconnected, but try to stay on the grid as far as feasible. So they try to help in recovering of the fault. How? Like the PV system can operate with the leading and lagging power factor, means that they can supply the reactive power. During the fault condition, generally voltage drops. Okay, so voltage, for example, if because of fault, voltage becomes 0.8 per unit. If the PV system can supply power, if it can bring the voltage again back to the 0.95 or higher, so it means things are done. So PV system need not to be disconnected. But if the voltage comes very low, it is difficult even for PV system to help. In that case, might be I have to disconnect. So it depends upon the situation. And then of course you can have some kind of backup. Although in the grid connected system you have the grid as the backup, but if the grid itself is highly unreliable, okay, and your solar power is not sufficient, you should have some kind of storage system, okay, so that there is sort of backup. Now we have to understand about the DC and AC rated power. This concept really very important. As we know that DC connected system consists of an array of modules and power conditioning unit that includes inverter to convert DC power from PV system into the AC required by the grid. Okay, so basically now a good starting point to estimate the system performance is that rated DC output of an individual module under standard test condition. So standard test condition, one sun insolation. One sun insolation means 1 kilowatt per meter square. One sun insolation means 1 kilowatt per meter square. Like as we say, 1 unit of electricity, it means 1 kilowatt hour. Some standard terms are there. If you say 1 unit of electricity, it means 1 kilowatt hour. So in this technical term, if you say 1 sun, it means 1 kilowatt is standard term. So AM is air mass ratio unless specified. The standard term is 1.5. Nominal temperature is 25 degree. So when a PV system is placed in the field condition, okay, so it may deviate from the standard condition. If the temperature is high, so the power output from the PV system will drop, as we have seen it. So in that case, we have to see that how much power we are going to produce. The AC power, what we are going to get from the PV system, the PV is generating DC. So you have the conversion efficiency. Okay. So this conversion efficiency, it does not only talk about the efficiency of the converters, but it includes several other factors as well. So one is of course the inverter, but what are the other points? Inverter efficiency, then if there is dust accumulated on the PV module. Okay. So how, much clean? Is it like a brand new? No dust at all? Even like say, how frequently you are cleaning the PV module. Okay. If too much dust, either you cleaning like 1 time a day or 2 times a day, or if it's less dusty in 3 days. So you see what is the optimal between the cost on the cleaning and like that. Okay. So you consider the some efficiency loss because of the dust accumulation. Then mismatch of the module, I will explain this term, mismatch of the module. And then difference in the ambient condition, ambient temperature. As you see that whether ambient temperature is 20 or 25 or ambient temperature is say 45. Okay. So it will have significant effect on the power produced by the PV panel. So even you have the full sun insolation, 1 kilowatt per meter square. So even in the full sun, because of the impact of these losses, the power output can be less 20 to 40%. Okay. So we already saw the effect of temperature variation. Now let us try to understand what are these losses because of the mismatch. This is very interesting concept, quite nicely explained. Here you can see that it illustrates that impact of slight variation in the module IV curve. We have the PV module. It can be from different manufacturers. Okay. Once you have PV module from one manufacturer, we want to have its expansion, then maybe some other manufacturer may be available. So basically you can see that because of the some mismatching condition, for example, you can have a PV panel rating say 180 watt. PV panel rating is say 180 watt. So one manufacturer supplies the PV power of 180 watt. One is supplying at say 30 volts, 6 amp. Okay. Other one is supplying at say 42 volts, 5 amps. Both PV panel have the same power rating. Okay, if one manufacturer you get 180 watt, then you got from the another manufacturer again 180 watt, but both have the different voltage and current ratings. You thought that power rating is same. Sometime non-technical people will come and they will say, don't worry sir, You should worry about the power rating. Power rating is same. So why you are worrying? We are here. Don't worry. It will operate excellent. They will confuse the expert people as well. Right? So if any salesperson comes, don't worry, sir. We will give you a little bit discount as well. Okay, don't worry, it will work better than your original one. No problem. So you'll think that this person will say, please be honest and don't, I'm poor guy, please, I'm just solely dependent upon you. Right? So this is how things works, Okay, don't try to cheat, please. So I leave it to you. So this is how things practically work. So you can see that this is we call that when you are matching, you not only match the power, but match for the, okay, I will take from you, match the power, match the voltage, match the current. Okay, no problem. Then you will see that that is a proper matching. If you have the power matching, voltage and current different, it is called the mismatching. Okay, so here you can see that both PV panel 180 watt. So theoretically, you think that 180 plus 180 connected in parallel should give you 360. Okay, but when you are connected them in parallel. Okay, so basically one is like say 36, another is 42. Okay, so it may end up depending upon like say delivering you some lesser power, maybe end up with 330. For example, one PV panel is giving you 5 amps. One PV panel is giving you 5 amps. Another is giving you 6 amps. So total current becomes 11. So current is 11, and then the voltage. Okay. So it will not give you certainly 360. So this is called as the mismatch. If you have mismatch, so because of this mismatch, there could be efficiency loss up to 4%. Okay, so little bit if we are not careful, so 4% gone. Okay, so just little bit careful that avoid the mismatching. So then we see that another term what we call here in other countries we call it STC, standard test condition. In US they have there's another rules, they call it PTC. So PTC stands for PV USA test condition, PTC. Very much similar but little bit difference. So here you can see that if we consider 1 kilowatt PV system under standard test condition, module, we talked about the term NOCT. What this NOCT stands for? Nominal operating cell temperature. NOCT stands for nominal operating cell temperature. So this considered as 47 degrees centigrade. So DC power output at MP peak drops 0.5% per degree above the STC temperature of 25. Estimate its AC power output under PTC conditions if there is a 3% array loss due to the mismatch of the modules. Efficiency loss of 4% because of the dust, and inverter has efficiency of 90%. So here just to explain you quick concept, based on the conditions we calculated the cell temperature. So cell temperature 53.8 degree, Then based on that, we calculated the power output because of the high temperature, how much power we are getting, 1 kilowatt into 1 minus the power drops 0.5%, 0.005. Temperature difference is 53.5 as we calculated here, minus standard nominal temperature, ambient temperature 25. So it gives us power 856 just because of that temperature variation from 1000 we simply come to the 856. Then different efficiency loss, whatever power we got 856, then efficiency lost because of the mismatch 3%, so 0.97, then 4% because of the dust, inverter efficiency 0.9. So overall you see it gives us 720 watt. Okay, although PV system we say that it is 1 kilowatt, keep in mind it is DC. Okay, then how much AC power you are expected to get. So what we are saying, then all these conversion efficiency loss, it is not only just inverter but some other factors, mainly the temperature variation. Okay, what it is saying 1 kilowatt, it is in the STC, like the what is your efficiency in the AC room, right? When you go in the field, it drops. Okay, same is the device. So when it is the perfect condition, then it is delivering 1 kilowatt. When you take it on the rooftop, 50 degree, 20% directly gone. So you can see that 30 to 40%, something like that, will be the drop in the power. So this we talked little bit about the PTC, etc. I am not going into the capacity factor, like you say that similar to what we call as the plant factor, plant load factor. What we have, for example, these conventional power plants, it can operate almost continuously. Okay, but we have constraint here, PV systems, how many days out of 24 hours, 6-7 hours. So its capacity factor is comparatively low. Okay, now when we want to have decide the sizing of the grid connected PV system, how we'll decide the sizing that we want to have the grid connected PV system we want to use for the commercial purpose. So where we want to install this grid connected system, so we can see that how much is the space available. For example, we have the different buildings, we want to use the space of the roofs of the buildings. Okay, so you have to see how much is the space available for us where we are going to install the PV system. Then we have to see how much investment we want to do that. Okay, we have to see how much even we can have huge amount of space available, but then we have to see how much initially investment we want to do. So we have to see that how much investment we are going to do. Then of course, if we have money, if we have space, but then again we have to contact the PV utilities, how much power they want to buy. Okay, so at least how much they are willing. So we have to consider these factors, that how much space available, how much money we want to invest, how much power utility are willing to buy. So all these things we have to keep in mind. Okay, once you know that annually how much energy we are going to supply, this much energy means kilowatt hour. Okay, so this much electrical energy we are going to supply to the utility. Okay, so that energy what you are going to supply for the utility in, for example, 1 year. Okay, in year you have got the 8760 hours, but then you have to see what is the capacity factor for PV system. As an average, for example, 6 hours, 7 hours every day, then you see how many hours you can have the PV generation. You consider that. So then you calculate the kilowatt rating of PV. Keep in mind that what kilowatt you are getting is AC, and then you have appropriately conversion, and then you decide the DC rating of the PV system. Are you following? AC and DC. I gave you example in the previous slide. Then based on that, then you see to get, say for example, 100 kilowatt, and then you have to select that, say in 1 meter square area how much panels you can have, spacing, all these things you can keep the calculation. Okay. Keep in mind, when we have system very big, then we have to consider some in between spacing may be required for maintenance purpose, etc. So you have to follow the standard guidelines. Then of course when you are selecting the components, PV panels, inverters, batteries. So again once you did the calculations, then whatever you are going to select, obviously you will select what is there available in the market. Okay, so inverters, how many inverters, what sizes, then also make the decision what is available in the market. So here when we are talking about the grid connected system sizing, so the design involves more around the non-technical parameters rather than technical parameters. So talking about the how much space available, how much investment capacity we have, how much is the buyer is willing. So decisions moves around these points. So this example gives you little bit calculation. I'm not going into the detail, but you can have these simple calculations that an energy efficient house to be fitted with the rooftop of PV array that will annually displace all the 3,600 kilowatt hour per year of electricity that house uses. How many kilowatt DC under standard test condition PV will be required, what area will be needed. If you have to make some assumptions, you can suitably make. So again you see from DC power you have the AC power. So considering the appropriate number of hours operation as an average, depending upon which place you are going to install, okay, based on some data, and then you consider suitable. First we calculate this is the energy, yearly energy. Okay, unit is kilowatt hour per year. Then from this we want to keep the term just like kilowatt. Okay, so for hour we divided by days, and then as an average how many hours PV can generate the electricity, 6 hours, 7 hours, 5 hours, depending upon the which place. So it gives you like the AC power 1.73, then DC power. So both DC and AC are related with the conversion efficiency. So you consider conversion efficiency including the efficiency of inverters around 10%. Then power loss because of the temperature variation, dust accumulation, if there is little bit mismatch. So all these factors you consider, maybe conversion efficiency 30%, 20%, whatever you decide, you consider. So it gives us the DC power rating, and then based on that you can calculate for this much of power how much area will be required, knowing the size of the PV panel and considering the other space conditions. Now we talk about the standalone isolated PV system. So when we are talking about the isolated PV system, we design, so technically it will be more complex. Okay. So here basically one main point we have to keep for the standalone system, more concerned about the backup. Okay, what kind of backup we are going to have for the standalone PV system. So generally we have the battery, but we can have the diesel generator which may be optional. So you have the PV system, charge controller, batteries, and then inverters. All these things we need to consider. We can have the diesel generator, maybe optional. Okay, so when we are going to design the standalone PV systems, where we are going to place, we need to know about the loads. Okay, like whether the standalone PV system is required for what application. Okay, it is for the domestic purpose, it is for some office purpose. So we need to know its occupancy, we need to know its users. Okay, what kind of load is there, we need to do the calculations for the load. So for example, you need to know the power requirement for, say, typical household, or maybe different types of load. How much is the power consumption? How much is the power consumption? What different types of loads you can have? For example, you can have the refrigerator. How much power it will consume? What size refrigerator? How much power it is going to consume? I could have dishwasher. Could have this for cooking purpose. If it is the gas, is fine. But if it is electric, so I have to consider its load. Then microwave, general households like the clothes washing machine, ceiling fan, air conditioner, heater, clothes, hair dryer, television, printer, in office printer, computer, laptops. If it is like the industry, what are the some other device? Okay, if you some multi-story building where you are going to use this PV system, you may have the lift as well. For example, little bit big office can have three lift, for example. Okay, so again you have to consider the diversity of the load. You know the diversity of the load. All electrical engineers know that all the connected load we are not going to use at the same time. We have the air conditioner, we have the heater, we are not going to use at the same time. The washing machine we are not going to use all times. Electric iron we are not going to use all time. So we need to have diversity, particularly when we are talking about the emergency load. For example, we have the normal supply, all the three lift might be operating. When we have diesel generator, then just basic, one lift is operational. Okay, so all lights will not be on, just whatever minimum basic you can manage to life going on, like that. So again you have to consider the diversity. If you want to have design for a building, you are the consultant. If you have already similar building, your things becomes easy. Or if you have information, all these informations you are going to consider for the isolated system. But we show that in case of grid connected, we need not to do all this stuff, because here we are just simply selling the electricity grid connected. Okay, and we just see how much we want to investment, how much is the space available, how much is someone is willing to buy. But here we have to make an estimate for the load, and then we have to consider backup. So in fact you see that isolated system requires more technical design. Okay, then in isolated system, some of the consideration, few I discuss, few more you can see, that in standalone PV system design begins with an estimates about the load that needs to be served. We discussed this point. Then trade-off between more expensive, efficient appliances and the size of PV and battery system needed. Like we can also see that whatever the load we have got, okay, partially we can have some partially DC load. If we can partially use DC load, so it can be directly supplied from PV system. We need not to have the converters. Okay, so that point we should be considering. Now, like the backup, emergency. Okay, so as I gave you example, isolated system, like for example, several story office building. So backup generator kind of thing, that what sort of fraction of load we are going to consider for the backup. When normal supply is not there, how much load we run on the diesel? Not the full load. Okay, then the diesel generator will be too much expensive. So how much is the essential load? It is people stay in the office, manage with like the fan, not like the AC. Some basic stuff is there. So one lift working, something like that. You see what fraction overall you have. Then one more important point, for example, when we have these motor loads. Okay, so motor load, you will see that starting current of the motor load will be high. Okay, so that what we call starting current, inrush current for the motor loads, that also needs to be considered. And then very important point, I would like to mention that what should be the sequence of connecting the loads. Okay, that how much current is PV system able to supply. Okay, so when you are connecting the load, first you connect the motor loads, because initially motor will draw the large current. You have got this space. Okay, motor starts, it takes high currents, we have capacity available, then it settles down. Then you have the static load, so that first you almost exhausted your capacity with static load, then you start the motor loads, so it will go above the rated current. So even sequence of operation is also important. So all these points needs to be considered. The list design is not exhaustive, but at least give you some basic idea. Then we are talking about the battery. In previous sessions, we have also talked about the battery. So when some topics comes again and again, it means this is really very important topic. So these batteries in PV system provide the storage, help meet the surge current requirements, provide a constant output voltage. There is a lot of interest in the battery research because of these electric vehicles as well. When we are doing the need for the battery, so several points needs to be considered, like the cost, weight, number and depth of the discharge, efficiency, temperature, performance, discharge rate, charging rates. So several important points needs to be considered. So broadly, we completed this chapter. Again, some of the important reference. Mostly I talked from this book. Very important. Please, at least every student, online and offline are physical. So it is very interesting. Which are actually present, they are offline or physical. So please download this 2003 version. At least you have some resources talking about the renewable, wind, solar, very nicely explained. Some other topics are also there. And then this the paper I mentioned, something talking about some stability challenges for large scale PV integration. You can see another good review paper talking in general some of the technical issues for PV systems. Some other research paper contributed by my students, kind of review papers. You can find several research paper as well in the literature. So we are just at the end of session. I will be happy we have some time. So it is basically from my side, whatever the contents I was expected to deliver, I have delivered, but we have some time. So I think we have some time to ask again some questions. I expect maybe one question as an average from every participants. Okay. So if not, simply say, hello, how are you? So you are done, eh? So at least I want to have, later you say I attended. So even the online student, we cannot see that, but we'll try to see that if the photo can be on, we can recognize some student, or at least see if they say I attended your course. So at least I can say, yes, I recall your face. Eh? So it is very important. So let us see, please try to just ask some question. In fact, generally I present another interesting topic, like we are all researchers, academics, either PhD student, master students, faculty members. Okay, most of us are academics. So for us, publication is extremely important, either PhD student or masters. So basically, publication, proper planning is very important. Okay, and for PhD or master student, so plan from the day one publication, because publication itself takes time. Okay, the process itself takes the time. Okay, so just see, first of all, just see what is your institute or university requirement. Okay, clearly find out what is the minimum requirement in terms of publication, what sort of publications are required, Scopus journal papers, SCI journal papers, what is the minimum requirement. Okay, so that minimum requirement should be completed. If minimum requirement is not complete, it means your thesis is ready, it can delay because of the that requirement is not complete. Okay, so first of all, just try to complete the requirement, then on the top of that you can publish more, and please always try some good journal. Keep confidence in you, have proper planning, and try to go not very high, but at least some good quality publication. So this is very important. And some of the things very important, like we are aware of all the ethical issues. Okay, like in the school time we say कि नकल नहीं करना, cheating नहीं करना, it is not good. Okay, but later when we become more senior, sometimes we forget little bit, knowingly, unknowingly, ethical issues, plagiarism issues. Okay, so basically when we have a paper, it is written by a researcher, faculty member, like any programming we are doing, we have the flow chart, if and then. If this yes, then we move to the next step, otherwise go back. Okay, so please keep in mind as a rule that you check the similarity before submitting any document. Okay, because sometimes student has written not by intention, but sometimes whatever reason there might be some similarity, there may be unnecessary problem. So please ensure that similarity check is done, and then basically analyze the similarity. Sometimes similarity might be coming high, but the means that it is not, we need not worry. When we go to the doctor, they say BP is high or temperature is high. So we cannot be doctor our own. Doctor will just see the reason for that. Okay, so analyzing the report is very important. Okay, so sometime high could be because of some unnecessary issue as well. Okay. So please have check for that. Then some of the recent stuff, Chat GPT. Okay, we thought that it will be very useful. It can be very useful, but if something is used sensibly, okay. But if you just use order the chat GPT, please prepare for paper for me. Okay. So like so basically that will not work. Okay. You need some assistant for something. So intelligently you can use, but we cannot be complete boss that okay, please prepare 2 paper by tomorrow for me. Right. So even when we are submitting any paper in the journal, first notice will pop up. Have you used the AI tools, Chat GPT, etc. Okay. So please be careful. Please stay ethical as much as we can, because when we are publishing, whether we will get the benefit or not, obviously we'll get it benefit. When we'll get, how much we'll get, that is the different story. But if we make some mistake, single mistake, knowingly, unknowingly, we can be in trouble. Okay. So it is always good that we are very, very careful about these things. So I know all understand, but still sometimes we mentor, we advise. So a few of the things, and so I just completed from my side. So I would like to thank you all. But please, if you have some questions, queries, please more than welcome to ask. So please, if you have some queries, questions, or we have other faculty members, so we'll see that how we are going to move forward further. Any quick questions from please, any participants? I have already given you my contacts, email, my phone numbers are there. So please, anyone is welcome to contact me. Stay connected. So I want to really thank you all for your great interest. When we are at the end of the year, most of people are having holiday. You are doing very hard work. And I want to give this, sincere thanks and their commitment, like this, all this team who are, helping this, making the material online. Okay. And so many teams members are involved, academics, students, drivers, food preparation, list is endless. Okay, I want to sincerely thank everyone for great hospitality, their great commitment. So thank you all. So it has been great for me to deliver this GIAN program. I hope you enjoyed. It met your expectation. Okay, so the learning is not completely finished. As I said that, I give several reference. If you need something more, then, we are stay connected. So please, I'll just stop here and then let's see how we continue further. Thank you all.